Welcome to the deep dive. Today, we're plunging into something really cool right at the heart of modern AI, the attention mechanism.
hmm
Specifically, how researchers found, well, a really clever technical shortcut to make it dramatically faster without, breaking anything.
That's right. Yeah, we've pulled together quite a sack of sources for this deep dive. Everything from inserts of a research paper preprint, introducing something called Sage Attention 2++, a study guide that tries to explain it, and even a technical FAQ.
Okay. And our mission to kind of cut through the complexity, we want to distill the, let's say, academic innovations behind this new technique.
Right.
Understand how they squeezed out this really significant speed up and see why it matters for the powerful AI models you might be using or hearing about.
Yeah,
Think of this as your fast track to understanding this specific cutting edge piece of AI acceleration.
absolutely. So let's start with the problem. Sage Attention 2++ is actually designed to solve. You know how AI models need to understand context?
Yeah, like in a sentence, which words relate to which other words.
Exactly. That's the job of the attention mechanism. It lets the model focus on the most relevant parts of the input data.
It's kind of like when you're trying to understand something complex, your brain doesn't give equal weight to every single word, right? It zooms in on the key concepts.
Yeah, it zeroes in on the important bits and how they relate. Attention does that for the AI. But here's the big challenge,
The bottleneck.
the bottleneck. The standard way this works, the computation required, it just explodes really fast as the input data gets longer.
Ah, okay. So if you double the input length,
The work quadruples. It's quadratic complexity. If you're dealing with a short sentence, it's, well, no biggie.
right?
But if you want the model to process a really long document, or analyze a high-resolution image, or maybe a long video sequence,
Then that quadratic scaling just kills
it
performance.
becomes a massive bottleneck, exactly. The standard attention mechanism just gets way too slow for big data.
So finding ways to make it more efficient isn't just like an academic exercise. It's absolutely critical for making advanced AI practical.
Totally. For real-world applications, you need this efficiency, and the field has been working hard on this. Our sources point to a few main ways researchers have tried to tackle this quadratic problem.
Okay, what are the main approaches?
Well, first you've got methods that try to fundamentally change how attention works. They aim for linear complexity, ON.
So the work scales directly with the data length, not its square. Much better.
Much better, yeah. Then there are also sparse attention techniques. These try to be clever and figure out that the model only really needs to look at some of the data.
Kind of cheap a bit by ignoring the less relevant stuff.
Sort of, yeah, processing only the seemingly relevant context.
Okay. And the third category.
That's where Sage Attention 2++ comes in. Hardware optimized implementations. These methods don't necessarily change the core math of attention,
Mm-hmm.
but they find incredibly clever ways to make the existing math run much, much faster on the specific computer chips they're using, like GPUs.
Ah, okay. So it's less about changing the recipe and more about using the kitchen appliances way more efficiently.
It's a great analogy. And Sage Attention 2++ sits firmly in that camp. The goal is superior speed, but keeping the accuracy and flexibility of standard attention. It builds on earlier work like Flash Attention and its own predecessor, Sage Attention 2.
Right. So Sage Attention 2 builds on Sage Attention 2. What was Sage Attention 2 doing first? What was its trick?
Okay, so Sage Attention 2, which itself built on the Flash Attention framework that used tiling and online softmax, clever stuff, Sage Attention 2 introduced quantization more heavily.
Quantization, using smaller numbers, right? Less precision.
Exactly. Think of it like using smaller, maybe slightly less precise measuring cups. Instead of standard high-precision numbers, they used lower precision 8-bit floating point numbers, FP8, for some key matrix multiplications or mapmuls.
So using FP8 math is faster on the hardware.
Much faster, yeah. Those specialized hardware units can crunch through FP8 calculations quicker. Sage Attention 2 specifically used this for the PV multiplication.
PV that's multiplying the attention probability by the value matrix.
Correct, and that gave them a nice speed up. They also quantized key and k, the query and key matrices, often using integer types like INT4 or INC8 for even more speed there. But the FP8 for PV was key.
Got it. So FP8 math equals speed. What's the big innovation in Sage Attention 2 then? How did they go even faster?
Okay, this is where it gets really interesting and quite technical, more academic, you could say. The core insight came from looking even deeper at the specific hardware instructions available on newer GPUs.
Like the machine code the chip runs.
Pretty much, yeah. They discovered there's a specific, even faster hardware instruction for doing FP8 matrix multiplication. Sage Attention 2 used an instruction that accumulates results in FP32.
accumulates, remind me what that is again?
Right. So when you do matrix multiplication, you're doing tons of little multiplications and then adding those results together, right?
Yeah.
The accumulator is like the running total where those subs build up as you go through the calculation.
Okay, the running total bucket. So Sage Attention 2 used FP8 math, but the bucket for the running total was FP32 big and spacious. That was already faster.
It was faster than using FT16 everywhere, yes. About 2x faster than standard FP16 math, according to the paper. But the Sage Attention 2++ team found this other instruction, mm.f16.f8.f16.
Whoa, okay, decode that for me.
It means do the matrix multiplication using FP8 inputs, but use an FP16 accumulator, a smaller bucket for that running total.
And that specific instruction is even faster.
Significantly faster. The sources say it offers potentially up to a 4x speedup compared to standard FP16 math. So double the speedup of the instruction Sage Attention 2 was using.
Wow. Just by changing the size of the intermediate bucket?
Essentially, yes. Leveraging that specific faster FP16 accumulator instruction is the core academic idea, the central innovation for Sage Attention 2++'s speed boost.
Okay, a 4x potential speedup, that's huge, but if it's so much faster, why wasn't everyone just using this FP16 accumulator instruction already? There must be a catch.
Ah, yes, there's always a catch, isn't there? And it's a good question. While the FP16 bucket is faster, it's also, like you said, much smaller than the FP32 bucket.
Right, FP16 numbers have a much narrower range they can represent compared to FP32, about negative 65,000 to plus 65,000.
Exactly. So even though the individual numbers going into the FP8 multiplication, the P and V values are already small because they're quantized.
When you start adding up lots of those multiplication results in the small FP16 accumulator?
That running total can quickly shoot past 65,504. It overflows the bucket.
And you lose information, get wrong results. Disaster.
Precisely. So the challenge, the academic puzzle for the Sage Attention 2++ researchers was, how do we use this super fast but annoyingly small FP16 bucket without it overflowing during that crucial PV matrix multiplication?
I mean, you can't just swap the instruction, you need a workaround. How did they solve it? What was the first part of their solution?
Their first solution is actually, well, quite elegant conceptually. They decided to make the numbers going into the FP16 accumulator even smaller.
Ah, shrink the inputs to fit the small bucket.
You got it. They did this by carefully adjusting or narrowing the quantization ranges for the P and V matrices. Remember, quantization involves scaling the original values. They tweaked these scale factors.
How did they know how much to narrow them?
They derived a constraint based directly on that FP16 range limit, essentially the product of the maximum absolute values they allowed for the quantized P and V had to be below a certain threshold.
Okay.
This threshold ensures that even when you accumulate the maximum possible sum the hardware does in one go, that running total won't exceed the FP16 limit.
Makes sense. Do they give an example?
Yeah, the paper mentions a specific constraint. PR times VR needs to be less than or equal to 2047, where PR and VR are the max absolute values for quantized P and V.
P times VR 2047.
Right, and they give an example pair that satisfies this, like setting the maximum allowed absolute value for P to 224 and for V to 9. That product is well within the limit.
That's a neat trick. Constrain the inputs based on the hardware limits to enable the faster path. Okay, but after doing the super fast math in FP16, you still need the final result in FP32 for the rest of the model, don't you?
You absolutely do. The rest of the network usually expect FP32 or maybe FP16, but FP16 accumulation was just for this internal step.
Isn't converting from that internal FP16 accumulator back to the required SP32 format add time back in? Like, does it eat into the savings?
It does add some overhead, yes, and minimizing that conversion overhead was the next challenge they tackled. This leads to their second key technical innovation.
Okay, what's the second trick?
They call it delayed FP32 buffering.
Delayed buffering. Sounds like you're just waiting to do the conversion.
That's exactly the core idea. Instead of converting each completed FP16 accumulated result to FP32 immediately after it's calculated, they cleverly accumulate two consecutive sets of results from that fast ma.f16.f8.f8.f16 instruction in the FP16 accumulator before doing a single conversion of the combined sum to FP32.
Ah, I see. So you do twice the fast FP16 work before you pay the cost of the slower FP32 conversion once.
Exactly. You effectively have the number of times you need to perform that conversion step, reducing its overhead significantly.
That's smart. But wait, if you're accumulating two sets of sums in the FP16 bucket before converting, doesn't that mean the bucket momentarily needs to hold potentially twice as large a value?
Sharp. Yes, it does. Which means
You need an even tighter constraint on the input numbers. That PR times VR limit needs to be even smaller now.
you got it. The paper states this requires roughly halving that previous threshold. So now PR times VR needs to be less than or equal to about 2047 divided by 2.
Wow, okay, so they needed really small inputs for this delayed buffering trick to work without overflow. Did they find values that worked?
They did. The paper mentions they selected PR54 and VR54.5 as a feasible pair that worked well.
224 and 4.5. That satisfies the tighter constraint.
Right, it allowed them to use the delay buffering trick while introducing what they found to be minimal error from the tighter quantization.
So just to recap the core academic innovation, spot the faster hardware instruction with the FP16 accumulator, realize it has range limits, solve that by narrowing P and V quantization, then realize the FP32 conversion is an overhead, solve that by delaying the conversion and accumulating twice, which requires narrowing P and V even more.
That's a perfect summary. It's really a sequence of identifying a hardware opportunity and then cleverly solving the cascading algorithmic challenges it creates. A beautiful piece of hardware-aware algorithm design.
Okay, so how is this actually implemented? What are the practical details?
It's implemented using CUDA, which is, the standard way to program NVIDIA GPUs where all this high-performance computing happens.
Makes sense. And they tested different versions?
Yes, they evaluated two main variants in the paper. The main difference was how they handled the initial QK transpose matmul, the first step in attention.
Right, before the PV multiplication where all the FP8, FP16 magic happened.
Exactly. So one variant they called Sage Apt ATN2++8, this used 8-bit integers INT8 for both the query queue and key matrices in that first step.
Okay. And the leather.
The other was Sage ATN2++4+8. This used even lower precision 4-bit integers INT4 for the query matrix queue, while still using INT8 for K.
INT4, that's tiny. Sounds potentially even faster, but maybe riskier for accuracy.
That's a very good intuition. Both variants, though, used the core FP8 approach for P and V, specifically the E4M3 format of FP8, with all the clever FP16 accumulation and delayed buffering tricks we just discussed.
Got it. So the PV part is the same. The QK part has two options, INT8 or INT4, INT8. How did they perform? Let's talk speed first.
Okay, speed. The headline number that really jumps out from the sources is up to 3.99 speed up over Flash Attention 2.
Wow. And Flash Attention 2 was already considered state-of-the-art for speed, right? So nearly 4 times faster than that is? Well, it's a massive leap.
It really is significant. Looking at the detailed figures in the paper, the SageAT ETN2++4+8 variant, the one using INT4 for Q, is indeed the speed king.
That's the 3.9x one.
Approximately, yeah. Around 3.9x faster than Flash Attention 2 when measured on hardware, like an NVIDIA RTX 4090 GPU.
And the 8+8 variant.
The SageAT ETN2++8 variant using INT8 for Q and K is also extremely fast, around 3.0x faster than Flash Attention 2 on the same hardware. Still a huge improvement.
So the version using the absolute lowest precision for GPU on Piece 4 alongside the core FP8 PV trick gives the maximum speed. And these tests weren't just like in one specific scenario.
No, they were quite thorough. They ran kernel speed comparisons across different GPUs, including the RTX 4090 and even looking forward to a potential RTX 5090. They tested different model configurations like head dimensions of 64 and 128, various sequence lengths, and tested both with and without causal masking, which is common in language models.
Okay, so it seems robustly faster across common use cases.
Yeah, what really stands out is that this isn't just a theoretical speed up on paper, it's measured kernel performance on actual hardware in realistic scenarios.
Okay, massive speed up confirmed, but here comes the big question, the one you always have with these optimization tricks. Did you break the AI? Does this incredible speed come at the cost of accuracy or the quality of the model's output?
That's always the crucial trade-off to check. And the sources are actually quite clear and positive on this. First, looking just at the attention mechanism itself, they report that Sage Attention 2++ maintains the same level of attention accuracy as the previous Sage Attention 2.
How did they measure that?
They directly compared the output tensor of the attention layer calculated using Sage Attention 2++ versus a high-precision baseline using metrics like code-mean similarity, relative L1 distance, and root mean square error, RMSE. The differences were negligible.
Okay, so the attention calculation itself is still correct. But the ultimate test is how the whole model performs on a real task, right?
Absolutely. You need to look at the end-to-end metrics. So does the language model still generate good text? Does the image model still create good pictures?
Yeah, did they test that?
They did, and quite extensively, they evaluated Sage Attention 2++ by plugging it into a really diverse set of powerful large-scale AI models.
Like what kind of models?
A real mix, everything from cutting-edge large language models like Llama 3.1
Okay, big name.
to state-of-the-art image generation models like Flux and Stable Diffusion 3.5,
Also huge names.
and even complex video generation models, mentioning CogVideoX, Humion Video, and WAN. So they really covered text, image, and video generation tasks.
That's impressive coverage. So how did the models actually do on their respective tasks using Sage Attention 2++?
The results were very strong. The paper reports negligible end-to-end metrics loss across this whole diverse set of models and tasks.
Negligible loss. Okay, what about the two variants? Did the slightly riskier INT4 version show more loss?
Exactly as you'd expect based on your earlier intuition. The SageAd ETN2 plus 8 plus 8 variant, the one using INT8 for Q and K, showed almost no metrics loss across the board. Pretty much identical performance to the baseline.
Wow, so 3x speed up for free, essentially.
Pretty much, yeah. The SageAd ATN2 plus plus 4 plus 8 variant, the faster one hitting that 3.9x speedup, did introduce, as they put it, a little metrics loss.
Ah, okay, so there is a tiny trade-off there.
A tiny one, yeah. But they still characterize it as negligible overall, especially considering the substantial extra speedup it provides. They measured things like perplexity and accuracy for language, ClipSim and ClipT for images, VQA metrics, FID scores for image quality, clip score, image reward, a whole battery of standard tests.
So you have a choice, basically. You can get a massive 3x speedup with virtually zero quality loss using the 8+8 version, or you can push for the absolute maximum speed, nearly 4x, and accept a tiny, often unnoticeable dip in metrics using the 4+8 version.
That seems to be the conclusion, yes. Either way, it's a huge win for efficiency, offering what they call plug-and-play acceleration.
Plug and play, meaning you can just swap it into existing models relatively easily.
That's the idea. Because it maintains the standard attention interface, but just runs faster internally, you can potentially drop this optimized layer into many existing models across different domains, text, image, video, and get an immediate speed boost without major architectural changes.
Okay, let's try and bring this home then. Why should you, the listener, care about all these deep technical details, FP16 accumulators, quantization ranges, INT4 versus INT8? Why does the speed up matter?
Well, because breakthroughs like Sage Attention 2 plus plus A, even though they're deep in the technical weeds, directly impact the AI applications you might interact with every day, or maybe the ones you're hoping to build.
How so?
By making a core component like attention run so much faster, it enables the entire model to potentially process more information faster. Think about it. Maybe faster responses from your AI assistants,
Okay, yeah. Less waiting.
or the ability for models to handle much longer conversations or summarize huge documents because the attention bottleneck is lessened.
Right, longer context becomes more feasible.
Exactly. Or generating higher resolution images more quickly, or creating more detailed videos in less time. Faster training times for developers too.
So it means the AI tools you use can potentially become more powerful, more responsive, maybe even cheaper to run in the long term because they're more efficient.
That's the downstream effect, yeah. All thanks to this kind of really clever innovation hidden deep within the technical architecture. It's a step towards making these incredibly powerful AI capabilities more accessible, more practical, more useful.
It really shows how optimizing these fundamental building blocks, even at the level of specific hardware instructions, can unlock totally new possibilities at the application level we all see.
Absolutely. It's not always about just making the models bigger. Sometimes it's about making the existing pieces run much, much smarter and faster.
So wrapping this deep dive up, Sage Attention 2++ achieved a really significant speed up in AI attention. The core academic innovation was leveraging a faster but trickier hardware instruction that uses an FP16 intermediate step and FP16 accumulator. They then cleverly solved the challenges this created, specifically the FP16's limited range and the overhead of converting back to FP32 using two main techniques.
Right, the narrowed quantization ranges for the inputs P and V to avoid overflow.
And that delayed FP32 buffering trick, accumulating twice in FP16 before converting, which required even tighter quantization.
Exactly. And the result is dramatically faster attention up to nearly 4x over Flash Attention 2 with minimal, often negligible, impact on the actual quality of the AI's output across a whole range of demanding tasks.
What's really fascinating, as you said earlier, is how that deep dive into hardware specifics, finding that one faster instruction, led to this cascade of elegant problem solving at the algorithm level to make it all work safely and effectively.
Yeah, it's a great example of that synergy between hardware understanding and algorithmic creativity.
It really makes you wonder, doesn't it, what other hidden potential is lurking in the specific designs of our computer chips, these GPUs?
Hmm.
How might creative researchers continue to uncover these deep technical opportunities, these little hardware quirks or features, and quietly change what's possible in the AI tools we rely on every day without us even realizing the specific technical magic happening underneath?
That's a powerful thought to end on. What other hardware capabilities are just sitting there, waiting for a clever academic insight or a smart algorithm to unlock their full potential for AI?
A lot to think about there. Thanks for walking us through that.
My pleasure. It was fascinating stuff.